For our MAE 152 project, we decided to model and simulate a TV wall mount. Here we have all the full assembly design iterations, iteration 1, iteration 2, and 3. The material of our TV wall mount is aluminum 6061 T6. For each design iteration, we applied 3 different loading cases, fully extended, 90-degree angle, and fully collapsed. For each model, we performed static analyses. Fixed restraints were applied to the holes of the wall mount component, and a load of 50 pounds was applied to the TV mount component. Here are the results of the static analysis. We also performed modal analysis to all models and compiled the results to this table. This is the frequency animation for mode shape 2 design iteration 3. Next, we have the wall mount component.
Here are the 3 design iterations for the wall mount. Iteration 2 removes material from the backplate and adds fillets. Iteration 3 cuts the thickness of the backplate in half. Removing material from the backplate in iteration 2 increases the maximum stress but reduces the maximum displacement. Cutting the thickness of the backplate in half further reduces the maximum displacement in iteration 3 and also brings the maximum stress down to almost the same value as the first iteration. The next component is the arm.
We performed a static analysis and placed a fixed restraint on one end of the hole and a load of 50 pounds on the other hole. A closed-form solution was calculated on the extension arm using the stress and displacement equations, along with the given values. The results show that the stress had a percent error of about 30%, which was likely due to a singularity in the static simulation, while the displacement gave a reasonable value of 6% error.
From the full assembly simulations, we found that the single arm extension in the top left image experiences the highest stress under all 3 loading conditions in all 3 design iterations. The highest stress on this part was 1.15 times 10 to the 4 psi, or about 80 megapascals. In most use cases, the TV mount would not be repositioned very often, maybe once a month. For an extreme case, we will use 50 cycles per day. The structure should also last a long time, so we set a lifetime of 50 years. This gives us a total of 912,000 loading cycles at 80 megapascals, leaving the part under the SN curve, proving that it will last its expected lifespan. Next will be the pivot.
For the pivot, we applied 2 different loading cases. In the first case, fixed restraints were applied on the side holes and a load of 50 pounds was applied in the 2 holes located in the middle. The second loading case switches the boundary conditions and load locations. In iteration 2, fillets were added. In iteration 3, the thickness of the backplate was reduced. In both loading cases, the max stress increased in iteration 2. For loading case 1, the maximum stress decreased in iteration 3 due to its ability to distribute the stress more effectively. For loading case 2, the max stress further increased in iteration 3, almost to the point of yielding. This is because the part experiences high stresses caused by the sharp edges in the fillets.
The iterations for the TV mount were based off of the locations of high stress and displacement values. Bits of material from the pivot connection piece were subtracted wherever high stress points are found. These locations moved within a small area throughout each iteration, along with increasing its stress value. The method for decreasing displacement was to change the shape of the faceplate to minimize the amount of material that was furthest from the center, as this was where the highest displacement occurred. That concludes our presentation. Thank you for watching.